So hello students, welcome back to our video classes, and this is the second part of metals and non-metals. So before coming to this part, I think you have watched the first part of this chapter where we were discussing about different types of properties of metals and non-metals, like the sonorous nature, like the malleability, like the ductility, all the things those are there specialized for the metals and the physical characteristics of non-metals as well. And there we have learned how to segregate the metals and the non-metals. Okay, and if you just go through the properties are literally very simple. But the thing is, if they ask you a question like, write the differences in between a metal and non-metal, then you just have to write the properties in the columns, right? So that's why I just skipped that part. Apart from that, I think you have understood all of it. Okay, so if you just go through it, and I have also given you the exceptions for all the characteristics, right? So the non-metals, all the characteristics, those are there for non-metals, and what are the exceptions for them? Okay, and for the metals as well, the names and the characteristics and the exceptions for them as well. So if you just go through it, then I think you would be able to understand all the physical properties of metals and non-metals. Okay, but today our topic is the chemical properties. So as far like the preliminary idea about the physical, the metals and non-metals, I think we have it. We know how to separate them out. If I have a metal, if I have a non-metal, how to separate them out. Okay, I know that with respect to the physical properties. But how do they react in real time with the different types of elements, with water, with acids, with different types of other metal salt solutions? Okay, and like how they react with the air. So if we just go through the chemical properties, you would be able to see some interesting features about them. Okay, so let's just start with the first thing, like what are the chemical properties that metals are showing? They are easily corrodable, they can lose electron, form basic oxide reacting with oxygen, have low electronegativities, good reducing agent. Alkali metals like lithium, sodium, potassium react vigorously with water. Magnesium reacts with hot water. Aluminum, iron, zinc reacts with steam, and these things reacts with water or dilute. Do not react with water or dilute acid. So all the things that those are written over here, they are just the concise form of whatever we are going to read today. Okay, so let's just start with the first thing. Okay, so the first thing, here goes the first thing, the metals. Basically, if you just look at the periodic table, so the periodic table looks like this, isn't it? If you just look at it, then you would be able to see that in the first section of the periodic table, there are two groups, group 1 and group 2. Okay, like lithium, sodium, potassium, rubidium, cesium, francium. Okay, and beryllium, magnesium, calcium, strontium, barium, radium. So these are the metals. Just remember one thing. The element that ends with is a metal. Like lithium, sodium, potassium, rubidium, cesium, francium, all of them contains in its name, isn't it? For that reason, we call them metals. We call them metals. Clear? Now, for the metals, I think like what are the speciality about the metals? When you would read this chapter, like the spectral periodicity, you'd be able to see that the metal are, I think you know about it already. The metals are the element that has 1, 2, or 3 electrons in the valence shell, isn't it? In the valence shells. So if you just look at all this, all these elements, if you just try to find out their electronic configuration, you'll be able to see that all of them contain either 1 or 2 or 3. Like here in group 13, so all of these elements, like these elements, the first group contains 1 electron in its outermost shell. The second group contains 2 electrons in its outermost shell, and the 13th group contains 3 electrons in its outermost shell. Okay, this is how they operate. Now, when they have these 1, 2, or 3 electrons in the valence shell, they are called the metals. Okay, so as they have 1 or 2 or 3 electrons, they are very much keen towards donating electrons. Okay, just give me a moment. Just a moment. Yeah. Wait. Yeah, you're back again. So they have a prone towards giving up the electrons. Okay. So for that reason, all the metals have a tendency to give up its electrons. So metals have a tendency to give up its electrons. Think about it. All the metals you have seen in chemical reactions, just think about sodium or think about potassium, all of them always they form the plus charge, isn't it? The cations are always metals, isn't it? Na plus, K plus, Ca2 plus, Ca2 plus, or aluminium 3 plus. All the time you have seen them getting the plus charge. Why is this happening? Because they are the one who is losing the electrons. They are the one who are losing the electrons. That's why we call them like that's why they are the one like they have a tendency to lose the electrons. Clear? So this is about the metals. Okay. Now, as they are losing the electrons, what are they doing? Look, electrons, the element that loses electrons, the reaction in which the electron is being lost. That is an oxidation reaction, isn't it? Here, sodium is getting oxidized to Na plus. Okay, as sodium is getting oxidized to Na plus and it is losing electron, this electron has a potential to reduce someone. So for that reason, metals are called very good reducing agent. Metals are called very good reducing agent. Have you got it? Why? The metals have a tendency to lose electrons, to get oxidized. And as they are getting oxidized, they are losing the electron. That electron is getting to someone else, going to someone else and reducing it. For that reason, the metal over there is called a reducing agent. Clear? So all the metals are reducing agent, very good reducing agent. So this was the first step. So first thing was metals have a very good tendency to lose electrons, and that electrons losing tendency is also called the reducing property of metals. Okay. Now the metals are like in the periodic tables, the group 1, the group 2, group 13. There are near about 90 metals in the group and the overall periodic table. So all the things like over here, like copper, zinc, scandium, vanadium, titanium, all of them are metals only. Okay, so most of the elements in the periodic tables are metals. Okay, and there are some non-metals as well. So near about 90 to 90, near about 90 elements are metals in the periodic table. Okay, now moving on to the next part. How do the metals react with water to form metal hydroxide and hydrogen gas? So to understand this thing, it's a very simple reaction. metals reacting with water to give you metal hydroxides and hydrogen gas. But there is so many things that you can learn from this reaction. Look, this is the way through which you can prepare the hydrogen gas. Okay. But the thing is, all the metals do not react equally with water. Look, the metals. Wait for a moment. Yeah. So I was saying is, metals when they react with water, they gives you metal hydroxides plus hydrogen gas, isn't it? This is how we prepare the hydrogen gas in the laboratory. Now the thing is, this reaction is not equally plausible for all of them. Not equally reactive. So the reactivity of the metals changes, and with respect to that, the reaction occurring over here, that is also changing. So there is a preference you can see over here. There is a preference. Like as we move from top to bottom, the thing which is happening is the reactivity is decreasing. So all I want to say is this one is the most reactive, the potassium, and the silver over here. So there is platinum behind, beneath it. That is going to be the least reactive. Clear? Now, how do they react with water? Look, if the reactivity of the metal is decreasing, now to make the metal react with the water, what we have to do? We have to increase the reactivity of water. So how can we do that? We can increase the temperature of the water to increase the reactivity of the water. If I can increase the reactivity of the water, then definitely even the low reactive metals can also react with them. Got it? That is the plan. Okay, we have to do that. Now, as you can see that we have started with potassium over here. So potassium or sodium when they react with water. When they react with water, the thing we get is NaOH or KOH along with hydrogen. Okay, we get NaOH and KOH along with hydrogen. Now, the thing is, this reaction is so vigorous and hydrogen is very inflammable. So it catches fire immediately. Immediately it catches fire because of this hydrogen, because being so inflammable. Okay, now this NaOH and KOH and this hydrogen is there, and being inflammable in nature, it catches fire. Fine. Okay, so for that reason, we cannot put in sodium or potassium in normal atmosphere. They would drag the like the moisture from the air, and they would react with it, and actually they would catch fire. They are very dangerous. So for that reason, we put them inside kerosene. That's why we put them inside kerosenes. But this water over here, this is normal water, because it is potassium, sodium, and calcium. When we move to magnesium do not react with normal water. We need water which is hot. Okay, magnesium only reacts with hot water. They do not react with normal water. When they reacts with hot water, it gives you this one. Okay, it gives you this one. When magnesium reacts with hot water. Okay, magnesium hydroxide and hydrogen gas. But why not magnesium? Why magnesium is not reacting? Because when magnesium is treated with normal water, what happens is we used to get magnesium oxide as a product with water, with hydrogen. Now, this magnesium oxide as a product that we are getting, this magnesium oxide, okay, this forms a layer over the surface of the metal. Okay, so it forms forms of layers over the metal surface. For that reason, the reaction is not proceeding further. Okay, the same thing happens for here. We use hot water. Okay, from zinc, we had to use steam, and for iron, we first what we have to do is, let's see if I have some pages now. So first we have to do is we have to make it red hot. After that, it would react with water. Okay, so like not the water, actually this is the steam only. Okay, so that is how you can make them react. After that, no one would react with water. Okay, no one can replace hydrogen, or no one can do nothing, right? So for that reason, this is the only, up to iron, sometimes lead would react with water. Okay, and would give you the hydroxide and the hydrogen gases. Okay, so this is how this reaction occurs. Now, the next thing is we are going to react metals with dilute acids. So if I take HCl as an example, so I'm going to get a metal salt plus hydrogen. Okay, so this is what is going to happen. Now the thing is, this reaction, the reaction you can see over here, this is happening only from HCl. If I take Zn plus HCl, I'm going to get ZnCl2 plus H2. Okay, but when the reaction is happening with H2SO4, or HNO3, you can use H2SO4 or HNO3, any one of them. Okay, now let me draw it over here. Both HNO3 and H2SO4, they just gets broken into the constituent particles like this. So this HNO3 and H2SO4, both of them are very good. They are very good oxidizing agent, as you can see, because you can see like when they just broken down under the influence of temperature, they just broken down into some oxygen atom that we call nascent oxygen. This nascent oxygen is very much reactive, that they can oxidize anything. They can oxidize anything. Now, for them, what happens is we get the result as ZnSO4 or ZnNO3 whole twice plus H2O, not H2 anymore. For them, we get H2O, not H2, because the hydrogen is getting oxidized over here. As a result, you get H2O for concentrated sulfuric acid and for HNO3. For dilute sulfuric acid, it would not happen. The product would be just the same, the sulfate and hydrogen gas. Fine. This was all about acids. Now, So for HNO3 and H2O, they would give you water, the oxidizing part. Okay. Now, okay. Now the fact is, the thing that I'm going to I'm trying to explain to you, is this reaction, this concentrated H2O and HNO3 reaction, all the acid type of reaction, they have a limit to which they happens. Okay. So, like as you can see, like more you go down the more you go down the table. Let me show you. Yeah, more you go down, the reactivity is decreasing. So as the reactivity is decreasing, the amount of the tendency of the metals to react with H2SO4 or HNO3 is also decreasing. For as a result, you not get the reactions you want. Okay. Just remember one thing. Yeah. Just remember one thing. This magnesium or manganese. Okay. Both of them, for magnesium and manganese, both of them, if they react with HNO3, they would not give you H2O. So they do not gets oxidized in these type of things. Okay. So from there, in front of them, we can make this thing, right? This hydrogen. Okay, not water anymore. So this is just pure hydrogen. So this was all about it. Okay. Now the thing is, yeah. So metals react with dilute acid to form the metal salts and the hydrogen gas. So you have seen earlier as well, when you take copper sulfate or those type of solution and zinc, the metal of zinc with it. Okay. So it gives you Zn sulfate and copper. Now the thing is like, just wait for a moment. This is H2SO4. Okay. What happens is you get the H2 gases out of it, right? Now, we would deal with this part, reactions with metals and other metals. So when a metal A is reacting with a salt of metal B, what happens is the salt of metal A and metal B. So what happens is, like if you just reacting with zinc and copper sulfate. So what would happen if you just react them together? Then what would happen is this cation would take this anion and this would remain as it is. So copper plus ZnSO4. Okay, these type of reactions are called displacement reaction or double displacement, depending on the type of reaction. Okay, so when what you're doing is you are taking a salt of a metal and you are putting your metal in it. Like consider this one, copper sulfate, and you are putting some iron in it. What would happen? As iron is over here and copper is over here, so iron is much more richer than copper. Okay, like more reactive than copper. What I mean to say is, so when you have this thing, iron and zinc with copper sulfate, what would happen is, so zinc or iron, whatever it is, whatever it would be, it would try to react and get to this result as soon as possible. Okay, now the thing is, it would only happen if the metal is placed above the another metal. Like let's consider, like I have a iron. I am in zinc, so in this here, in this position, and I am reacting this thing with copper sulfate. The reaction would happen. Okay, the reaction would happen. Zinc plus copper sulfate reaction would happen. So what would be the result? So copper would be all left all alone, and zinc would react with H2COSO4 to give you ZnSO4. Okay. So when the element you are choosing as a when the element you are choosing, if that has higher reactivity than the other one, okay, from which it is just replacing, I can replace my junior, not my senior. So the element those are above that thing, okay, in your life. So you can think about it then, okay. You can make this reaction happen about this decomposition, displacement reaction and all, okay. This is how it occurs. This is just because of the metal activity series, okay. You just try to remember it. Now, how do the metals react with air? Okay, so when the metals react with air, they mainly reacts with the oxygen one, and it would give you this, okay. Like if I take sodium and if I just react them together, I'm going to get Na2O, okay. I'm going to get this, and okay, so metal oxide, so sodium plus oxygen is giving me Na2O, okay. Now if you just put it in water, what would you get? You'd get NaOH. You'd get NaOH. So for that reason, we call these oxides at the basic oxides. Fine. They are called the basic oxide because they are basic in nature. But yes, there are some metal oxides like Al2O3, it is amphoteric in nature. এগুলো হচ্ছে amphoteric in nature. So the thing is, like if you take this Al2O3, it would react with both acids and the bases. It would react with both of them. When Al2O3 reacts with acids, it would give you and when Al2O3 reacts with, wait for a moment, and when this Al2O3 would react with NaOH, another base, okay, what would happen? I would get Na2AlO2, okay. When Al2O3 reacts with NaOH, we would get Na2AlO2, sodium aluminate. Okay, we call it sodium aluminate. So these are called the amphoteric oxide. There are some metallic oxide like Mn3O7, okay. So these are basically metal oxides, but still they are acidic in nature, okay. But still they are acidic in nature, I mean, although it's a metal oxide. So now coming to this part, why metals are called electropositive elements whereas non-metals are electronegative. So the metals wants to give up electrons. For that reason we call it electropositive element, and the molecules that takes up the electrons, that is called the non-metal. So the non-metals are the electronegative element. That is why we call them electronegative elements, okay. Metals are electropositive elements because they can form positive ions by losing electrons, right? Non-metals are electronegative because they can accept it, okay. Explain the reaction of copper with silver nitrate solution. So if you take copper along with silver nitrate, if we just go through the chart, you'll be able to see that silver is below copper. Exactly, okay, plus Ag. So what would happen? So this is a displacement reaction because you can see copper and Ag, the position of copper and Ag, if you just compare them. So copper is over here and Ag is over here. So if they react, then obviously copper is going to replace the salt of Ag. Okay, so copper is going to replace this Ag, okay, to place himself over there. Okay, let's forget about this one because the question is not there. Okay, so yeah, that's about it. Okay, so just I think you can go through it now. Okay, you'll be able to understand all of it. Okay, study your textbook and refer to this video. And if you have any doubt, you just write it on the forum. Definitely, someone from our side is going to reach you. Okay, that's it for today. It was nice meeting you. I think I'm going to see you in the next video as well. And until then, just stay safe and keep learning from Ask Guardians. Thank you, everyone, and bye.